Alright, back with 100 Days of ML. It's day 84. Gonna continue with paper a week today, specifically reading Rashmon curves and volumes. So I think where I last left off, I just read the introduction and the abstract. So I'm gonna begin with reading the first section of the paper. Let's see. So he has a related work, and he has set definitions and notations. So I'll probably get through related work and a little bit of section 3, which is the definitions and notations. But yeah, again, today is the day of my final, so I want to keep this stream extremely short. So I'll give myself around like 10-15 minutes, and at the end of that, whatever I finish is whatever I did for today. Okay, so I'll open up the paper on my screen and go ahead and mute myself and continue taking notes on my iPad. All right, I'll start reading. Okay, just finished up related work. It sets up the definitions for a lot of the concepts that are going to be discussed about in this literature, specifically like what Rashmon sets are. Um, it's mostly like the set of active models that can be compared. And this definition has been used by different like authors in different ways. Here, what they're going to do is use it to define a metric to basically compare models with. And then it talks about the flat minima or wide valleys, a very popular way to, um, I guess, compare the performance of a model. It's also used to, um, I guess, make a model learn, especially neural networks, dense layers. We use something called the gradient to calculate towards like a minimum local minima or a global minimum, and this was essentially give you the greatest accuracy with the least amount of error. And they say that the Rashmon set can perform a similar computation. So in statistical learning theory, Rashmon ratio provides a certificate for existence of a simple model that generalizes rather than being a simplicity measure itself. So the Rashmon ratio kind of provides as a metric to compare different models rather than being a model that simplifies the models itself. There's a lot of talk about other like statistical, um, I don't even know what to call them, like concepts, I guess, like error flatness and all of these other Gaussian complexities, PAC Bayes theorem, covering number bounds, margin bounds. I have no idea what these things are, and I feel like I should definitely learn them. So, what I'll do is make some sort of list of concepts that I am not aware of, and maybe I can read some sort of article on them after this paper a week. And finally, model selection talks about the Rashmon curve and how it's going to be used to choose between models. And there have been different metrics to do this, essentially measured through the VC dimension, which I also don't know what they are, or the empirical clovers. They choose models that minimize risk within a hypothesis space, and the Rashmon curves do the same thing. But it seems that it used to it it uses universal it's universal among data sets. So I think that just means like having one data set, these values can change, whereas the Rashmon curve can stay consistent. I think I'm gonna call it here for today. If I start this now, I don't think I'll have enough time to essentially finish it. I'll end up somewhere in the middle, and the set notations look pretty difficult. I mean, they look pretty complex, so I think it might take some time to actually decode. I'm pretty sure it's important because it sets up the rest of the paper. So Yeah, this paper looks like a pretty hard read, not gonna lie. And there's a lot of pages. No, I guess whatever this is, supplementary information gives definitions of the things that were introduced. Something to look into. Definitely does not introduce everything, but some things are here. For example, VC dimension and I guess it's just VC dimension. And error flatness. I think that's what it means by epsilon. Anyways, okay. Let's wrap things up here. Okay, with that, I conclude 100 Days of ML. I'll be back tomorrow to continue reading.